So to show phase change, I'm going to use the TV diagram because that is my favorite diagram. That's the diagram I think is most logical for us to kind of think about first, because it has a line of constant pressure on it. So let's just consider this line of constant pressure that I'm going to be following here is 1.014 bar or 14.7 psi, which is atmospheric pressure. Let's consider wherever you're at right now. Let's consider it's atmospheric pressure. We're going to look at what's happening. And we're going to put liquid water, H2O, into a piston cylinder. Okay, and I'm saying right now that we're going to put it at 20 degrees Celsius, which is all liquid, and that would be represented here by this blue dot on this diagram right there. That's the blue dot. Now what I want to do here is I want to say that anything here that's in that liquid state, I am going to call it a compressed liquid. Okay, I'm going to call it a compressed liquid. I could also call it a subcooled liquid. Subcooled liquid. Or I could just call it a liquid. There's really three names for it: compressed liquid, subcooled liquid, or a liquid. Now, why is it called a subcooled liquid? Why is it called a compressed liquid? Well, if you look at this, where our saturation occurs at this point F, we are going to be cooler. That point is at 20 degrees, the point is at 100 degrees Celsius. We are cooler than that. We are colder than that, so that's where we call subcooled liquid. If you look at the specific volume is less than that, so we can say it's a compressed liquid. So that's where those two names come from, but I'm very comfortable with you just saying it's a liquid. But I want you not to get confused when you see this other language here. So here's what we're going to do. We're going to take that liquid that we have there at 20 degrees Celsius. So you can do this along with time if you want to. Take your computer into the kitchen, get some water out of the tap. If you let it sit there for a while, it's going to be about 20 degrees Celsius room temperature. And now what I want you to do is I want you to heat it on the stove. Now, of course, your pot is not going to be a closed system, but so let's look at this as a closed system. Yours is going to be an open system. The mass, the vapor, is going to be able to evaporate. But what's going to happen here is as we heat this up, we're going to be moving from point L to that saturation state. Okay, what's happening is the temperature increases considerably while the specific volume increases slightly. And you recognize this. You know that when you put a pot of water on the stove, you're going to increase its temperature considerably. It's going to go from 20 degrees to 100 degrees Celsius, or from 70 degrees Fahrenheit to 212 degrees Fahrenheit. And in that time, the specific volume is only going to increase slightly. If it increased a lot, you would have to say, okay, I'm going to put this much water into my pot, but I'm going to have to make sure that my pot's huge, because as I'm heating it up, that water is going to rapidly expand. This doesn't happen here because the specific volume only changes very slightly during that process. Okay, so that's what we're noticing here on our piston. We're going to bring ourselves to that point F that's highlighted by the blue dot. Okay, now we're at that point F, and that point F, and always with the subscript F, we are going to denote as a saturated liquid. So saturated liquid is going to have a subscript F, always, always, always. Okay, now that's a tipping point there. We're now at that tipping point because now if we add more heat, to that, we're not going to expand this anymore. We're not going to raise the temperature anymore. That's what I was saying. We're not going to raise the temperature anymore. All the heat transfer now added is going to be put into changing the state, changing it from liquid to a vapor. Okay, so that's where that tipping point has happened. Now we're as liquid as we really are, and now as we add more heat to it, now some of that liquid is going to change into vapor. Okay, now as we do that, as that vapor is created, now our specific volume is going to change considerably as we're moving across this line. We're moving way across here, or maybe halfway across here, and more and more vapor is formed as we add more and more heat. This isn't, again, why we don't represent heat and temperature as the same thing, because here we're adding heat to a system. The temperature is remaining the same for that water, but the phase is being changed because now the heat is not being put towards temperature change. It's being placed towards changing the state of that liquid. Okay, we're going to continue on as we go further and further along until we're going to reach over to that other side of the dome. But anytime we're inside that dome, we're in the two-phase liquid vapor region. Sometimes we have a lot of liquid, sometimes we have a lot of vapor, but that's going to slowly change as we reach across this dome. Okay, now, when we go all the way across, we are going to reach a saturated vapor. But we have to understand where we are here in the middle of this. We have to do because here the temperature is 100 degrees Celsius and the pressure is 1.014 bar, or the temperature is 212 degrees Fahrenheit and the pressure is 14.7 psia. We cannot say that temperature and pressure are independent here. We need to know something else in this region to tell us where we are, and we're going to call that quality. Quality is defined as the mass of the vapor over the total mass. I'm going to say that again. It is the mass of the vapor over the total mass. Students all the time want to say it's the volume of the vapor over the total volume. It is not true. Quality is defined as the mass of the vapor over the total mass. Okay, now let me go with this for a while, and I want to understand how we deal with quality. And I'm going to open up my OneNote because this is a very important idea. So we have said that we have a mixture X. We have the mass of the vapor all over the mass of the liquid plus the mass of the vapor. Okay, or we can say this is equal to the mass of the vapor over the mass total. Now what I want to use here is I'm going to want to use the nomenclature that we're going to be talking about in this class. So vapor state is going to be equal to G, and the liquid state is going to be equal to F. That's what I've determined. As you go back here, and let's look over here at the desktop. What we're defining the saturated liquid state is F, and the saturated vapor is G. And it's important to note that in this two-phase mixture, this liquid water and this water vapor, all the water vapor is saturated vapor, and all the liquid water is saturated liquid. Okay, they're just mixed up into pieces there. And so as we go back here to look at this, I'm now going to write quality is equal to mass of the vapor all over mass of the liquid plus mass of the vapor. All right. Again, it's important to understand that all the liquid is saturated liquid, and all the vapor is saturated vapor. Now, let's talk about how we can compare this to volume. Okay? The volume of the mixture, total volume, is going to be equal to the volume of the liquid, which is VF, plus the volume of the vapor, VG. All right? Now, we don't want to talk about this in terms of volume. We talk about this in terms of specific volume. So, what do? I divide this by mass total. Mass total. Mass total. So now what I have is the specific volume of the mixture is equal to the volume of the liquid over mass total, the volume of the vapor over mass total. Now, what can I say here? I can say the volume of the liquid is going to be equal to the specific volume of the liquid times the mass of the liquid. And I can say the volume of the vapor is equal to the specific volume of the vapor times the mass of the vapor. That's just the definition that we had back there in chapter 1. Volume is equal to specific volume times mass. We can do that by the units and understand how that goes. Okay, so I'm going to take these definitions, VF, and put it into here, and VG, and put it into here, and see what we get. We get the specific volume of the mixture total is going to be equal to VF MF all over mass total plus VG mg all over mass total. Okay, now remember what we said our definition of quality is. Our quality definition is going to be mass of the vapor all over total mass, okay, which seems to be right here. Okay, this is equal to x. And if we say the mass of the vapor over the total mass is x, then we can say that 1 minus x is equal to mass of the liquid over the total mass. Okay? Remember, this x can only go between 0 and 1. 0 means there is no vapor in the mixture. It's all saturated liquid. 1 means all the mixture is all liquid. So if we can calculate what we have for the ratio of the liquid over the total, or sorry, the vapor over the total, 1 minus that has to be everything else. Okay, so I am going to take advantage of this and plug that back into this equation, and now say that the specific volume total is going to be equal to VF times 1 minus x plus VG times x. And now doing some algebra, the total specific volume is going to be equal to VF minus VF times x plus VG times x, or the specific volume total is equal to VF plus x times VG minus VF. And this is a very important equation. I call it the quality equation because it helps us determine what the specific volume of our liquid vapor mixture is as we're going across that line, dependent upon the quality. Okay, and if you want to look at this graphically, which I think is important to be able to do, if we look at this TV diagram and we said that our quality was 50%, well, 50% is going to be right here, 50% of the way from a liquid to a vapor. Okay, how does this work? Well, look at it graphically. We're going to say we're going to find out what is going to be, this is going to be VG. So we're raising, this is going to be the distance, sorry, VG, VF. This is VF. Okay. Then what we're going to do is we're going to take VG minus VF, find the whole distance of this line, VG minus VF, so that's this thing here, and we're going to find out what percentage of the way we're across that. So if we say we're 50% of that, that's when we're going to add that to our VF. And that's where we find out where a property is. So we are going to use this, we have to use this quality equation. Anytime we're in the vapor dome, we're going to use this quality equation to find out what the specific volume is. Now, the question might be, well, how do I find specific internal energy? Same way. We're going to use that. We would use the specific internal energy total is equal to the internal energy of the saturated liquid plus the quality times the internal energy of the saturated vapor minus the internal energy of the saturated liquid. That is what we will find. Okay, the quality equation. It's on your equation sheet. You don't have to remember it, and it'll be something that you're going to use quite often, and we'll practice that as we get going through this semester. Okay. I told you here saturated liquid states is 0, saturated vapor we're going to go 1. So what we're going to do here is we're now going to take our system that we're somewhere inside here and we're going to continue to heat it up until we reach the other side of the dome, which is going to be represented by G, saturated vapor, and now all of our system has turned to vapor. Okay, X is now equal to 1. The quality is equal to 1 when we're there. Now if we took that point and we continue to heat the vapor, which we sure can, we can continue to heat the vapor, we are going to superheat that vapor. We don't just have a vapor, a saturated vapor. Adding more heat to it is going to superheat the vapor, and what's going to happen is now we're no longer doing any phase change, so now that heat transfer is going to increase the temperature and increase the specific volumes as we're going up here. So we're going to move ourselves up there. All right? Superheated vapor states that we're going to be talking about. Okay, now that's where I want to end this. We'll go down and look at your steam tables, how this looks in our next segment.